Okay, so we're going to be moving into CAMs. So we're going to be looking at designing CAMs and also the kinematic analysis of those. And that's what Chapter 9 is dedicated to. So, so our objectives for this chapter are first and foremost to identify the different types of CAMs and followers that are out there. All right. And there's a number of different kinds, but what we're gonna you know, speak to and look at the most common types. We want to understand the benefits of different types of followers when we have CAM motions, and then also construct a CAM follower displacement diagram as well as the profile of the disc itself. So this is going to be the CAD work that we're going to end up doing. So a CAM, first and foremost, is going to accept an input of motion and it imparts a resulting motion on what we call the follower. If we look at figure 9.1 on page 223 in our book, I'm going to go underneath. That's this illustration right here, okay? Here, what you're going to notice is we have an engine valve train. Here's our valve going up and down. And there's a valve spring, and then also the valve stem. The valve stem is in contact with the rocker arm, which then is in contact with the cam shaft. Now, the cam shaft rotates around, and this out kind of protrusion here is called a lobe. And as that cam shaft rotates around, as the follower, the rocker arm, comes in contact with that cam itself, and then as this rotates, as this lobe comes around, it's going to push that rocker arm down, which is going to rotate about this center. That rocker arm in turn is going to push down on the valve stem. Okay. And then as it continues to go past it, the rocker arm with the help of the spring is going to stay in contact with the profile of that cam, and it's going to go back up into the position that we see here. Okay. And then as this rotates around again, it's going to come back down and go up. And this is all about timing. Okay. So knowing how fast that camshaft is going will then time out when that valve is going to be going up and down at strategic times to you know, engage with the operation of the motor. So so a camshaft or a cam on a camshaft and the follower, these two portions right here are what we're most interested in designing in this particular chapter or this module. Okay, so we're going to focus on those two places. Now, a cam can impart very distinct motion to its followers, and in some cases, it's the only way that we can impart motion. So a lot of times where it's difficult to achieve with a linkage, as we've seen in the past, or the most common types of linkages to get motion to be done, cams can do this very efficiently and quite cost effectively. Cams are used in factory automation and a lot of different operations. We see them in engines because they sequence displacements in a very, again, cost-effective manner. Now, there are different types of cams, okay? And the different types of cams can be seen on the following page. So in figure 9.2, we're going to notice that there are a number of different types of cams here. Now, these are for the most part disc cams, and you'll notice that in the middle of each one, or I shouldn't say in the middle, really not in the middle, you're going to notice that there's a place that we can insert a shaft and a key or some way of making sure that that cam is going to rotate with or in sync with the shaft itself. Okay. So here you're going to notice this is where the shaft would come through. This is where the center of rotation would happen. And then as this rotates around, it would be in contact with a follower similar to like that rocker arm. And then it would impart motion for the follower itself. Many times that motion is going to be converted, if you would, from a rotational to either a pivoting or a linear type of a motion of whatever that follower is going to be doing. And then you'll see the other ones here as well. Now, down here at the bottom of the first column, we can see a couple of different types of cams. The first one being a plate cam. A plate cam is probably the most recognizable and most popular that's out there. And you'll notice that the cam profile here is always going to kind of be that unique kind of lobed looking type of profile. and it'll come in contact then with a follower. Now there's going to be different types of followers. We'll see here that this one actually has a roller on it and it's pivoting. Okay. The next one here, this is a cylindrical cam itself, and then there's a groove where the follower actually follows along as that cam rotates. Then the follower is going to go in and out along that path. And then the last one that we have here, these are actually two linear cams where we have linear motion going horizontally, converting it to vertical linear motion based on the if you would, the path or the trace path that peg is going to take inside of that path, inside of that plate. Okay. Now, with cams, there are a lot of different types of followers as well. And there's a couple of, canned ones, if you would. So the follower types and the follower shapes that are most common are going to be over here in the second column. So the cam is this portion right here that is going to be rotating on a cam shaft. And then the follower is going to be then the output motion, if you would. The cam is always the input. The follower is going to be the output. So the follower in this case is going to be what we call an inline follower because its center line is in line with the center of the rotation of that cam or the cam shaft itself. Okay, so if we extend that all the way through, it is going to be in line. And this is going to be a knife edge because of the point that we have here. And it's going to then reciprocate up and down, within the follower that we have there. The next one that we have is going to be a pivoting. Now the pivoting it just means that it is going to rotate, the follower itself is going to rotate about a fixed center. So in this case, it's going to pivot about that fixed center, and then it has a roller on the end of it that'll be in contact with the cam itself. Now, something that's real key here in the operation of the cam and the follower is that they have to constantly be in contact. Okay, they have to constantly be in contact. So there's going to be, now these are simplistic illustrations, but there's going to be ways and means, if you would, that's going to occur. And if we go back to that first illustration, that's the purpose of the valve spring here, is to keep that rocker arm in contact with that cam. Okay, so that it never leaves that surface. So even though we see these out here, there are going to be additional mechanisms and parts that are actually going to keep the follower in contact with the cam itself. Okay. The next type that we have is going to be an offset type of an arrangement. And all that means is that compared to the rotating center of our cam, our follower has a distance or offset between those two. So in this case, this is going to be, this is like a flat face follower that's going to go up and down, but it's offset from that actual center. And then the last one that we see here, this is another pivoting, but this time we have a spherical edge instead of a roller on the end of it. Okay, so, and these aren't the only types of followers, but they're the most common types and kind of the classifications, if you would, of. So they can take a lot of different forms actually. Now, as we look at the follower motion itself, it's going to be one of two things. It's either going to be translating. That means it's going to be in a straight line, which we saw in a couple of those cases, or it can be swinging or pivoting, as we saw in a couple of those cases as well. Now, follower position, as we said, it's either going to be in line or it's going to be offset. Okay. And so in line is when that follower is in line, and if we extend it, it's going to go right through the center of where that cam is rotating. If it's offset, then there'll be a distance between those two. We already looked at follower shape. There's the knife edge. This is the simplest form. It does create high contact stresses because all of the force is going through that one point. Okay. It does wear rapidly, and it is rarely used unless it's for very low speed applications. Okay. Roller followers, those remain in constant contact with that cam. They are the most commonly used. Friction and contact stresses are minimized because it's a rolling surface on the profile of that cam, but they can jam easily when there's steep displacements. So you got to be careful in using those and how fast you go. The flat face followers, they can take on steep cam displacements without jamming. They can also take quick motion changes. But they do have high friction forces, and deflection and misalignment can also be caused there as well. And then additionally, we have that spherical faced cam, and it can be used when we have steep cam displacements without jamming because of the spherical end on it. The radius compensates for deflection and misalignment, but again, the friction is higher. So all of these kind of have pros and cons, and depending on the application will depend on, which type that you're going to focus on. When we're doing our examples, we will know the kind. It'll be identified when we're creating the profiles and such. So prescribed motion. So the amount of time that is required to complete a full cycle, and that's going to be all the way around, is called the total time. Okay. Now the total time is going to be adding up the different intervals with the type of motion that we need to achieve. This will make more sense when we do our example in just a bit. Additionally, we need to calculate what the angular speed that is required for our cam. So what is that W? That W sounds familiar to us, angular speed or angular velocity. And that's going to be, we do 1 revolution, okay, around that cam. And we're going to divide it by the total amount of time that we actually need to achieve that. So when we look at all the different motions that we're trying to achieve, what is the total amount, okay? And we're going to divide that in 1 revolution to figure out, okay, what is the angular velocity or the RPMs that our cam needs to rotate, okay? And then lastly, what is the number of degrees beta per individual motion? So we're going to take that angular speed and we're going to multiply it by however many seconds that it needs to occur. And then we're going to multiply it again by 360 degrees. And again, this will make more sense once we get into an example. Jacob.
So if W is RPM, how do you get RPM if it's divided by seconds?
It'll be converting. So you will see that in the example that we do. Yeah. Because W, we know that we need to, like, for instance, if we need to size a motor or we need to, whatever, we need to tell somebody like, what is the rotational speed of something? We want to do it in RPMs because that's the most common units. But we're going to find that we're going to do in revolutions per second when we're using it in here, because we're going to be dividing 1 revolution rather than by minutes. Seconds makes more sense. So you'll kind of see, like I said, some of these this will definitely make more sense once we go through this first example. So we're gonna look at example 9.1 in our book, and it is already worked out, but I want everybody to pull out a piece of paper and we're going to go through each one of these steps, because this is going to be the start of many of the problems that you're going to be doing, and getting this experience then just helps to just make sense of the process a little bit more. So we're going to do this together. So I'll go underneath and we're going to look at the problem. Okay. So this is page 226 in your textbook. All right. So it says that we have a cam. This cam is going to be used for a platform that will repeatedly lift boxes from the lower conveyor to an upper conveyor. So here is the cam itself. Here's going to be the center of rotation of that shaft. And as this rotates around, this lobe then is in contact with our follower. Okay. Now, as we look at this, what type of an arrangement is this? Is this inline or offset? It is offset, yes. And how do we know that it's offset? Go ahead, Eric. Yeah. Yeah, so this is our follower right here. Here's the center line of the follower, about, right? And you'll notice that if I extend, it's not going to go through the center of rotation for that cam. So yes, this is an offset. Now, what about the follower type? Can you identify what that follower type looks like? It does look like a roller, right? Exactly. So, I mean, I don't know for sure, and I don't think that this actually tells us that it's a roller, but it appears to be a roller on that outside surface. Good, 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 good. You'll notice that the spring is here. What do you think that spring's job is to do? It's to return the follower and to remain in constant contact with the profile of that cam. That is really important. That profile or that follower absolutely needs to do that. Okay. So springs are very common mechanisms that we use in order to do that. And yes, it's going to then allow this to go up and down. Sometimes it can get stuck in the up position, if you would, if there isn't enough weight in that follower to make itself back down again. So the spring is going to aid in doing that. Okay. So you'll notice that this is going to go up and down. There's a lower platform and upper platform, and it's moving these boxes or these containers from the lower to the upper. Okay. Now, as we look, the prescribed motion is directly below here. So it's 5 steps. It says we're going to rise 2 inches in 1.2 seconds. Okay. So all that means is from its original position, it's going to go up 2 inches. Okay. And it's going to only take 1.2 seconds to do that. Then it's going to dwell up there, meaning it's a dwell is just, it's going to stay in that position. All right. Then it's going to fall 1 inch in 0.9 seconds, and it's going to dwell again for 0.6 seconds. And then it's going to fall another 1 inch or back down, if you would, to home position in 0.9 seconds. Okay. So this is the motion that we want to occur. So what we need to do, and I'm going to jump over to the end over here of the problem, because I think sometimes it's nice to know where are we going with this. In the very last part of this problem, this is a displacement diagram. Okay. I want everybody's attention. The displacement diagram is what's going to be used when we actually create our CAM profile. Okay. Now, what you'll notice about this displacement diagram is on the vertical axis, this is going to be the follower displacement, and in whatever units we're working in. Now, in this case, we have inches, and it said that follower displacement, it needs to rise 2 inches. That's what its largest value was to get it up to that next level for that conveyor. So you'll notice here that our highest value on here is the highest value for the displacement that we're going to have. So 2 inches is the high number there. Along the axis, then the horizontal axis, what do you notice? There's a bunch of stuff going on there, but what is one thing that you notice about that horizontal axis? It shows 360 degrees, which is going to be equal to 1 revolution. Okay. So this displacement diagram represents 1 revolution as we go all the way around that cam. Okay. Now, if this were, for instance, if we go back over here, if this was a constant diameter going all the way around here, okay, as just a circle that was offset from that center, that would mean that this would go as at a flat line the entire way, because that follower wouldn't move, right? But because of the lobe that this has, this is what, as this rotates around, this is what's going to allow this to go up and down and up and down. And so as we look over here, that's kind of what we're looking at. We're looking at a graphical representation of that distance or displacement that's occurring for that follower as it's going to be in contact with that lobe as it goes around 1 time. Okay, 1 time. All right. Anything else that you notice on there? So yes, this is 1 revolution of that cam, 360 degrees. Anything else you notice along there? What do you think those T's mean? Capital T. Time, exactly. Now, as we look back over here, you're going to notice that they gave us 5 like zones, if you would, around 1 revolution, where we had a rise, we had a dwell, we had a fall, dwell, and then fall 1 more time. Okay. Now you'll notice that the rises equal the falls, because we can't rise, or I'm sorry, we can't fall more than we rise. So those always have to equal, but they don't have to be the very same sequence on the opposite side. So as we look here, we're actually doing 5 distinct motions within 1 revolution. And each one of those is during a prescribed time. So those T's, so T1, for instance, is the very first motion that we have. That's how long it's going to take us in the full 360 degrees to do that rise of 2 inches. Then you're going to notice that we dwell for 0.3. That's going to be our T2. So if we go over here, right after T1, there's T2. We're going to dwell. That means we're going to stay in the same spot for a little bit. And then once we've stayed in that one spot, now we're going to fall. That's going to be our T3. We're going to fall for 0.9 seconds. So as we go here, T3, we're going to fall 1 inch during that time frame. Then we're going to dwell again. That's T4. And then when we go and we fall the rest of the way, we're going to be at T5. Whatever you start at, which is 0, you have to end at over here. If you end up having any like gap in there, then you did something wrong. Okay. Because again, you can only fall as much as you rose. You can't go down below this line. Okay. Now these displacement diagrams are going to be drawn to scale in AutoCAD. All right. So we're going to be able to, plot these out so that we can measure the distances. Okay. And then displacement diagrams are going to be used to actually create the profile of the actual cam. Okay. The first part of this chapter is just looking at, let's get the displacement diagrams for a prescribed motion sequence. Okay. It's getting that done first. And then once we have that in place, now using it to then draw out and physically make the profile of that cam is going to be the second part of this chapter. Okay. So today what we're going to focus on is that first part. And the next time we get together, we'll focus on the cam profile part. All right. Okay. So let's kind of get back to the beginning here now that you know kind of where we're going with this. So the first thing we need to do is we need to calculate the time for a full cycle. Okay. So the time for a full cycle, one cycle is 360 degrees all the way around, 1 revolution. So I need to add up each one of these times. Okay. So as we look at this problem, say example problem 9.1. Okay. We know that this is step number 1, the summation of the times. Okay. And they call it TI. I'm not exactly sure why, but capital T, the summation of the capital T I is going to be equal to T1 plus T2 plus T3 plus T4 plus T5, because there are 5 motions here. My expectation is everybody's taking notes because this is important. This is the process you're going to go through. So to do that, now we're going to put our values in, and we use the values from the prescribed motion that's given here. So for the first rise of 2 inches, it says in our problem that's going to take 1.2 seconds. So directly below T1, we're going to put 1.2 seconds. Okay. Plus, and we're going to do the next one, 0.3, even though that's a dwell, that's part of our rotation. So that's going to be plus 0.3 seconds plus 0.9 seconds plus 0.6 seconds. And then our last one is 0.9. Okay. So the summation of our TIs, then the total time for 1 revolution around our cam will be what? 3.9? 3.9 seconds. Okay. So 1 revolution is going to take us 3.9 seconds. And I believe that's the very next thing they have us calculate. Now we're going to calculate the rotational speed. Okay. So our W is going to be equal to 1 revolution divided by the total time it takes to do the prescribed motion that we have there. Okay. So here is our equation in variable form. We're going to keep 1 revolution up there because it's going to be the cam going around 1 time. So the 1 always stays on top, divided by 3.9 seconds. So 1 divided by 3.9 seconds, it's going to be 0.2564 revolutions per second. Now, keep that one kind of handy, all right? Because we're going to use it for our betas in a little bit, but we always want to convert this to RPMs because we have to know, okay, what is maybe the motor that we have to get, or we have to know what our RPMs are going to be. So we always convert this to revolutions per minute. So we know there are 60 seconds in 1 minute. So our W is going to be equal to, I'm going to put 2.564 revolutions per second, but it's also going to be equal to, if we multiply that by 60, 15.38 RPMs. Okay. But this one, we're going to want to know. And this is of the cam. This is the W of the cam. Okay. Always convert to RPMs, but again, we're going to be using the revolutions per second in just a minute. Okay. Any questions so far? All right. So now, as we look over here, what we want to figure out is, okay, how many degrees is each one of these going to take? So our first motion, which was T1, we knew that that was 1.2 seconds, but how many degrees does that equal? Okay. And that's what beta is. So beta is how many degrees of rotation do I need to take up for that motion? Okay. So to me, the easiest way to do that, well, I should say they're doing it down here. So beta is going to be equal to our cam rotation times the time. All right. Now, if we take the RPMs here, because our time is in seconds, we're going to have to do another conversion back again. So instead, notice that they use the revolutions per second here. That's why I said keep that one handy, calculate that one, and then multiply it by the number of seconds to get how much of a revolution. And then we're going to multiply that by 360 degrees. So, oopsie, wrong way. So step number 3 is we're going to figure out how many degrees does each one of these intervals take up on one full revolution. So our beta 1 is going to be equal to W of our cam multiplied by our time number 1. Okay, our time number 1. So we know we're going to take 2.564 revolutions per second. Okay, not the revolutions per minute, because our time is in seconds. So if we go back up to our time, T1 was 1.2 seconds. Okay, seconds cancel. So that means that when I take that number 0.2564 and multiply it by 1.2, my beta is going to be equal to 0.307, but it's revolutions. Okay, so it's about a third of a revolution that we're taking up, right, with that first motion. But if I want to actually plot it on my displacement diagram, I need to know how many degrees that takes up. Okay, so to do that, I would do a conversion of 1 revolution, 360 degrees. Revolutions will cancel out, and my beta 1 will be equal to 110.7 degrees. Okay. And you would do that then for each one of them. Okay, we're not going to do that in this example, but just because they're up there. But that's how we would do it. Do you guys? Does everybody kind of understand that process and the conversions that have to occur? Okay.
If you take it, second total, so for you would already be at 110 degrees at 1. So you're just adding. So for number 2, would it be 1.5 seconds, or would it be?
Oh, no, you would then do, yeah, let's look at that in just a second. Before we go there, let's just make sure. So when we look up here on our beta, okay, notice that it covers, now they got 110.5, we got 110.7, but again, probably rounding error because they always do their 3 significant digits. But now beta 2 is going to be the distance between there. So how many seconds is it just for that one interval? So up here, you're going to notice they take the 0.256 revolutions per second and multiply it by just the 0.3, which was our time 2. Okay. And then they got 0.077 revolutions, which then multiplying by 360, they get 27.6. So then that would be added on to the next part here. Okay. And then you would continue to do the very same thing. So then beta 3 is going to be that same number in revolutions per second, but this time times 0.9, and then converted to 82.9 degrees. So beta 3 is right here. Okay. And so on. Then would be 4 would be another dwell. And then 5 would be the last fall. And again, you're always ending up, you're starting at 0 and you're ending at 0. All right. And then the next revolution, you're like starting back over here and you're going through that very same process again. Okay. So it's all about timing. Okay. Other questions that you have so far as you look at this?
The T1, is that 1.2 by 1.28? I think I wrote it down. 1.2.
T1 was 1.2. 1.2 seconds. Yeah, you get that from the prescribed motion. Maybe. Okay. All right. So that's the first example to show you how you would plot a displacement diagram. All right, displacement diagram. So again, that's always the first step, if you would, and those are going to be the first couple problems that you're going to be doing for your homework. Now, we're going to move into, we really didn't look at like what we call follower motion. Okay, and follower motion is going to help us to construct what these lines look like as we go up and down based on the type of motion that it is. So the next section we're going to look at after this example is going to be follower motion schemes. Okay. So again, we've looked at already the displacement diagram. It represents that motion desired in terms of distance on that vertical axis and angular displacement on that horizontal axis. And we saw it in a couple different ways, by degrees, but then also by time. Okay. Displacement diagrams give that graphical representation of the motion that will be used to generate the profile of the cam. Okay. So they must be drawn to scale. So that's why we need to do them, very accurately, and CAD is the best way to do that. Now let's look at follower motion schemes. So there's a wide variety of different motions that are available for moving our follower. The objective of these schemes is to produce a movement that is smooth, with smooth accelerations, meaning we don't want something real jerky, okay, as it goes through. When we have slow moving cams, you can have high accelerations and they're not going to be a huge factor. So you can do some more of the simplistic type of motions that we're going to see. But when we've got high speed applications, then we really have to be cognizant of the type of motion that we prescribe to be sure that we don't have problems with jamming, vibrating, not being in contact, things like that. Okay. All right. So as we look, there's going to be some terms and some variables that we have to be aware of, and those are listed here, but they're also found starting on page 227. So it's kind of worth looking at them underneath here. Okay, so I have them in that PowerPoint, but they're also here and have a little bit more information. So first of all, H is going to be the total follower displacement. If we go back up to the example that we just did, H was, for instance, the total distance that we went for the rise, okay, which ended up being the total amount of displacement that we had on here. But then you would have an H related to any falls as well. Your H's on your rises always have to equal your H's on your falls, okay? Capital T, total time period for a rise or fall interval under consideration. Okay, and they really should have added here dwell as well. So we notice that up here on this axis, the horizontal axis, these capital T's corresponded to the different motions, including dwells, not just rises and falls, that occurred in a full revolution. Okay, so we had our rise T1, we had a dwell T2, a fall, a dwell, and then a fall the rest of the way. Okay, each one of those had a time associated with it. Okay. Lowercase t, this is going to be the time of a rise or a fall in an instantaneous mode. Okay, we don't use small t very much. Usually we're interested in the chunks of motion. So capital T's are what we see most often. The next one here is going to be beta. Beta is going to be the rotational angle of that cam for one of those motion sequences. So for instance, we saw how if we had a T1, in this case, it was a rise of 2 inches. We also had a beta 1. How many degrees of that cam did we take up? Okay, so that gave us our answer in degrees. All right, T was in time, this was in degrees, beta. All right, and each one of those sequences along the way, or those steps along the way, are going to have a corresponding beta or number of degrees of rotation that are going to be taken up. Okay. The next one here is going to be the angle into the rise or the fall interview that's defined by an instantaneous follower properties. Again, as far as displacement diagrams go in the CAM profile, this one is not going to be used as often, but we do see it in some of the equations coming up. And then you're going to notice that we have W, which is the speed of our cam, okay? And this is going to be in degrees per time. So whether that is in per second or per minute, you know, just kind of depends, all right? What we're using it for. And then the next one that we have here is delta R. This is going to be the instantaneous follower displacement at any time given in, you know, an angle or a time frame. So our R would be, what is that distance? It really relates back to that total H as well. It's a distance or displacement. We can calculate also the straight line velocity at any given point in time and the acceleration at any given point in time, right? So those are the different variables that we're going to see come up in equations that we're going to be looking at. Now, as we look at different motion schemes are going to give us, you know, different results in terms of how we're going to displace the actual follower itself. Now, there are 4 that we're going to focus on, which are the 4 most popular. The first one is called constant velocity, okay? What that means is that there's no acceleration, right? And it's used for low speed applications. If we look at figure 9.7, okay, you'll notice that we have above here, this is going to be our constant velocity motion curves. The first motion curve here is going to be our displacement to our, you know, and it goes along in that same displacement diagram type of fashion, where going to the right would start out with 0 degrees, if you would, and then we would continue on, you know, going in a rotation on that cam. So you'll notice that it's a very simple curve, if you would. It's really a straight line, and it's going to start out from where it is, and it's simply going to be a straight line going to where it ends, okay? Now, as we look at the velocity, constant velocity means that instantaneously we turn on and we are going at whatever that velocity is, and then we instantaneously turn off, okay? And what it also means here is that we don't have acceleration, okay? It's not very smooth, okay? Because it's an on and an off, an on and an off. And so it's hard to achieve. I mean, truly, when you turn something on, there has to be a little bit of a speed up there. It's not like instantaneous, but in theory, that's exactly how it's designed, okay? Not used very often, but for low speeds, okay? Something that you can be sure that even if it is going to be on right away, that it's not going to cause a jerkiness where something's going to come out of contact with the profile of the actual cam itself. So, well, is it a repetitive?
Could it be repetitive?
It could be, but again, for very low speeds, just because of the nature of the non-smoothness of it. And we'll kind of see in comparison to the ones that are coming up, how it does, they're better in that sense, if you would. The next one that we have is called constant acceleration. Okay, constant acceleration. We're going to turn the page, and those curves look like this. Okay, so as we look at distance curves wise, you're going to notice that now we're getting a rounded in of the corners. Okay, so as we go in and as we slow down. All right, and already you can imagine those are better for staying in contact with the cam, but then also for vibrations or any jerkiness that might occur, okay? You'll see here that we have a ramping up effect of the velocity, which is more, close to what actually happens in real life. But we do have the accelerations then being turned on and off and on and off, okay? So an improvement on the constant velocity, but still not necessarily desirable for all applications. Again, kind of sticking on that low speed side of things because of the abrupt changes in acceleration and or velocity. Now, to construct it in a displacement diagram situation, we would use this method right here. We aren't going to be doing this one for our homework, just again, because it's not a very common one, but you'll notice that we look at half of whatever the rise would be here, and we would divide it into, I think it's 1, 2, 3, 4 sections. And then we construct and we see where the intersections are. And those are going to be points that we're going to be putting in AutoCAD through a best fit spline, if you would, okay, in and out. The next type of motion is actually, I'm going to go back a second here because they introduced it over here. This is going to be harmonic motion, okay? The last two that we talk about are the two most popular, which are going to be the two that you're going to do for your homework, okay? So harmonic motion, and we're going to skip over to page 231. Here you're going to notice in a harmonic, this is the rise and this is the fall. Again, doesn't look much different than the constant velocity or the constant acceleration because we've got the curves coming in and out on either side. So if we kind of compare these two, here's the constant acceleration. Here's the harmonic. They look very, very similar. Okay, displacement wise, they're not very different at all. But what we will see is a difference in the, achieving of the maximum velocity. You'll see that's more of a curve here now. And then we also see an improvement in the acceleration as opposed to it being like straight lines, in and out. But you'll notice that on the initial in and on the out of the rise or the fall, there is this abrupt change, which is one of the disadvantages again. So you have to be really careful keeping that follower in contact because of that jerkiness that can occur here. Okay, now to construct this on a displacement diagram, this one we will be looking at, like I said, it's going to be part of a homework problem that you have. For instance, you'll notice right here, we've got a total rise. So on that last problem that we did, our total rise was 2 inches. We need to draw this to scale. Okay, it was 2 inches. So that means that at the 1 inch mark, as we look at this as 2 total inches, that's going to be the center of the radius that we create. And that radius that we create is going to be a 1 inch radius or a 2 inch diameter, if you would, arc here on one side. Then you're going to notice that we are going to be breaking this into 6 equal segments. So if we've got 180 degrees here and we want to break it into 6 equal segments, how many degrees would we need to rotate each one of those line segments? How many?
20 degrees.
30, actually. So 30 times 6 is 180.
Oh.
Yeah. That's okay. So, so it will be 30 degrees between each one of these evenly. Then what we're going to do is we're going to mark whatever your time period is. It doesn't have to be to the even degree increment. We're just going to divide this length along that x-axis into 6 equal divisions. Okay. And then from left to right, we're going to correspondingly put 1 through 6. And then as we start at the bottom here, each one of those divisions is 1 through 6. Then we're going to bring over and we're going to find the intersections of each one of these values horizontally corresponding to their vertical. And then through each one of those points along, we're going to have a best fit spline. Okay. So again, CAD does that really nicely for us. Sure.
Right.
It's going to be, yeah, it's going to be a best fit spline through those points.
I had to make one of those in Creo. It's not very easy.
So easy in AutoCAD. It'll be the best. Eric is going to love it.
Creo and point, for whatever reason, Creo doesn't allow you to put like regular points. Like
Oh, I don't know.
So you
Yeah.
can put it like manual sketches and stuff.
Yeah, no, this really, it's actually really easy in AutoCAD, quite honestly. So, So that's how you would construct that along the displacement diagram side of things, okay? And then it would just be the mirror image, if you would, on the fall side, all right? So that's harmonic motion. Then the last type of motion that we have is called cycloidal, okay? Cycloidal motion. And as we look at the curves for that, this one is going to be, again, the displacement curve doesn't look all that different, okay? But as we look at our velocity and our acceleration curves, you'll notice that here is like the answer to all of our problems, okay? But it is going to be the one that we use most often because especially of the acceleration here, that we don't have those abrupt changes again, like we do with the other ones, okay? Now to construct the cycloidal, here is going to be the method that we use. Now this is a little bit different. We're going to start at the top of our rise along our horizontal axis, and we're going to draw the line straight down through the zero where it starts, and then extend it to what would be the center then of the circle for the cycloidal motion curve here. The radius of that circle is going to be the total height divided by 2 times pi. Okay, so they give you that. Then what you're going to do is you're going to divide this into 6 equal sections. And then here again, along however far we're going to be going with our T or our beta, we're going to divide that into 6 equal sections. And then we are going to then extend each one of these up and then find the intersections and then create the best fit spline along that curve, okay, through those points. Any questions about that? Okay, so what these are creating on our displacement diagrams, these ins and outs, okay, along here, okay, and constructing those graphically, in our case, using AutoCAD, okay. Let's see where we're at in terms of our PowerPoint. Okay, so we did harmonic, we did cycloidal, and we've got 2 examples here, okay? So let's look at example 9.2, okay? And we're just going to focus on steps 1 through 3. And then we're going to plot the displacement diagram using CAD construction, and then include the appropriate labels, titles on the diagram as we see in the second part here. So as we look, starting on page 234, here we have the problem statement. It says we have a cam is to be designed for an automated part loader as shown, okay, down here. Using the motion equations, construct a chart that tabulates the follower displacement versus the time. We are not going to do that, okay? So what they're referring to over on the right-hand side is writing an Excel spreadsheet to tabulate that, okay? That's not going to be our focus, all right? We're going to instead go to constructing it graphically using the methods that we just saw, okay? All right. So also plot the data from the prescribed motion for the application. So here are our 4 steps. We're going to rise 50 millimeters in 1.5 seconds using a constant velocity motion. Now, as I said earlier, that's not a very common one at all. Okay. But again, they probably have a low speed application or just using it, you know, to show the process. Then we're going to return in 2 seconds using cycloidal motion. Okay. Then we're going to dwell for 0.75, and then we're going to repeat. So essentially, we really have for our prescribed motion on our cam 3 steps here. We've got a rise, a fall, and a dwell. Okay, rise, fall, and a dwell. So we're going to use the first 3 steps here. The first thing they're going to do is they're going to calculate the total time for that cycle. The second, we're going to determine what our rotational speed is of our cam. And then we're going to determine our betas, or how many degrees we need for each one of those motions. Okay, so let's go ahead, and I know these are here and we can point at the numbers, but you get a much more rich, full experience when we do these, because so often when you have that blank piece of paper, you're going to be like, how do we do that again? How do we get started? So this is example problem 9.2. Okay. And what we want to do, step number one, is we want to figure out what is that total time. Okay. Total time. We call that a cycle. Okay. That it actually goes through. A cycle is going to be one revolution. All right. So we're going to go look back up at the steps that we need this to take. So we know that we have a total time. So we're going to do summation, and then we're going to call this Ti, because that's what they use in the book. I don't know what the I means, but it does. We have a T1 for the first step, plus T2 for the second step, and then plus 3 for that third step, which is a dwell. That is a step within the revolutions. So when we look at the time here, our time 1 is 1.5 seconds, okay, plus our time 2, which is 2 seconds, plus our time 3, which is 0.75 seconds. So our total time to do all three of those, I have to add them up. You get 4.25 seconds. Yep. Okay, cool. 4.25 seconds. So step number 2, we now want to determine what is the rotational speed of our cam? What is the rotational speed of our cam? So our W of our cam is going to be equal to 1 revolution, okay, of that cam, because that's all of that motion has to happen in 1 revolution, divided by the total time that we need to go around that 1 revolution. Okay. So we're going to have 1 revolution divided by 4.25 seconds, right? So it looks like that's going to be 0.2353 revolutions per second. Okay. Now I always like to do that one because it's going to come in handy when we do our betas. Okay. Or our angles per interval. But we also want to convert this to revolutions per minute, because that's going to be the more common way to refer to our W. So our W of our cam is going to be 0.2353 revolutions per second, but it's also equal to 14.12, I guess, RPMs. Okay. With this one being the one that we're going to use in our next step. Questions so far? All right. Then our third step is we need to figure out how many degrees of rotation are each one of these steps taking up. Okay. So our beta is going to be equal to our W of our cam times that time interval, okay, of whichever one we're looking at. So if it's beta 1, it's going to be the W of the cam, the rotational speed of the cam, times time 1. Okay. So we'll do that one. We'll do beta 1. It's going to be equal to our W of our cam times time 1. So we're going to use the 0.2353 revolutions per second. Okay. And we're going to multiply that by the time for number 1, which was 1.5 seconds. Seconds cancel, and our beta 1 should get 0.353 revolutions, right? So that means it's a little over a third of a revolution, but we want to know how many degrees that is, right? So we need to do one more conversion here, right? So we know that 1 revolution is 360 degrees. So our beta 1 should be 127.06 degrees, right? Is equal to beta 1. Okay. Everybody get that same thing? Yeah. All right. Beta 2. That's going to be equal to, now, this is going to have the same rotational speed, right? So we can say it's going to be 0.2353 revolutions per second, but this time our time is going to be 2 seconds. Seconds cancel. .4706, and that's going to be revolutions. And we want to convert that to degrees. So we're going to say that 1 revolution, 360 degrees, revolutions cancel, and that would be 169.4 degrees. That's going to be our beta 2. Okay. So now as we look at these two, we take 127 and we add that, we're at 296.42 degrees. Okay. You could simply take 360 minus those two numbers, or you could calculate the third one. It's totally up to you. I think either one is valid because the dwell is going to be on the rest of it. So what I'm going to do is I'm going to say beta 3 is going to be equal to 360 degrees minus 127 minus 169.4. You get 63.6 degrees as your beta 3. A 0.1, again, yeah, just a little bit of rounding. Okay, so now what this gets us is, if we look at, and I'm just going to sketch it right here, we look at our displacement diagram along this axis right here. We know that this is 0 degrees and this is 360 degrees. Okay. We know that for 120, right? This is going to be our, actually like this. So I'm going to say for 127 degrees, I'm sketching. This is going to be our beta 1, right? Between there and there. Then we've got for another 169, so 127, 169.4 plus. So for 296.4 degrees from here to here, this is beta 2, right? And then our last chunk here is beta 3. That's the difference. That's the 63.3. Okay. Does that make sense to everybody? And then as we rotate, 360 becomes 0 again, and then we're going to go through that very same cycle. Okay. 1 revolution is all 3 sequences here, or 3 steps. All right. Now, for the first part here, it said that we're going to be rising 50 millimeters. 50 millimeters is about 2 inches, right? A little over 2, or a little bit less than 2 inches, huh? A little bit less than 2 inches. So we're going to, our high point here is going to be 50 millimeters. Okay. Now, the motion that it said on step number 1, it said that in 1.5 seconds, 50 millimeters, or in 127 degrees, this was going to be constant velocity. Okay. Constant velocity. So what that means is if I put this all the way up, okay, and that's where that ends, constant velocity is a straight line from the beginning to the end. That's as complicated as it gets for constructing it. All right. And we saw, though, that especially when we look at the velocities and the accelerations, not desirable for higher speeds. This can be for a low speed application, but for higher speeds, not a great idea. But that's what the motion scheme is for this one. Then immediately we're going to start to fall then back down in the next 169.4 degrees. Okay. All right. Now on this side, though, we actually have to construct this because this one said we are going to be falling, with cycloidal motion. Okay. Cycloidal motion. So it's not a straight line this time. What it is it's going to be the construction of this. Okay. but it's going to be on the opposite side. So we have to figure out what is the radius? What are these values? And then we would plot it out and find the intersections. Okay, so on this side, then we would divide into 6 sections. So this would get divided into 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6, just in the section that we are analyzing. All right, so not to the very end, because the very end is going to be a straight line right here down at the bottom. This is a dwell. Okay, our total fall is going to be just in this section here. So what that means is, as we come down, so our 1, 2, this is our middle, right? This is our middle. And right about here is our middle. We're going to go through here, through here, through here, and we're going to construct our circle to have its center right down there. Does that make sense? I'm just kind of sketching the process right now. That's what I want you to kind of get the idea of, because you'll be doing this in AutoCAD. Okay. What was that? It isn't bad. And the book does a good job, especially if you look at the construction illustrations. I think it's
Like if you had 50, I think that. Like if
Oh,
you had
yeah,
50,
yeah. Yeah, they're 3 and 4s. They're 3 and 4s. That's about it. Yeah. Like different steps. Yeah.
I don't think I can get about 5. Right? Unless there's some that have like.
Maybe. Yeah. But the ones that you'll be doing will just be a couple steps. Yeah. Yeah. So now you'll do your cycloidal, and then you're going to create the construction as we see here. Okay. So we'll do our 0 and 6 degrees, or I'm sorry, 0 and 6. You're going to have then this evenly distributed into 6 sections in 30s all the way around. Just got to remind myself. So 1 is going to be here. So we have to go in the opposite direction. 2, 3, 4, and 5. And then you're going to notice that they meet at the middle, top and bottom. And then what you're going to do is these are going to go up to go along with. So this is going to be our 1, 2, 3, 4, 5, and then this is 6. And then as we come through, each one of these is going to intersect with their corresponding 1, and so on. I don't know. Let me see here. This is going to be parallel along here. This is going to be parallel along here. I go in the opposite. I think I went in the opposite direction. Right. No, I'm right. 1, 2, 3, 4, 5, and 6. And then they come in the middle here. So 0, 6, and 3 come from the center. So as we cross over, 6, 3, and 0 are going to be these points right here. 5 and 4 are going to be along here. So here is 5. It would be parallel. 5 is going to be right about there. 4 is going to be along that line there. And then 3 we have already. And then 1 and 2 are going to be along the other ones. They're going to be along here. So 1 here, again, they're not straight, and then here. So these will kind of come in like this and then go down like this. I'm so sorry, Jonathan, you're like seeing nothing. Okay, but straight lines, much better constructed along here, as you can see. So everything comes from the centers of, okay, and then they intersect with their corresponding section going up. Okay, and then the total rise is going to be whatever, or fall, whatever is prescribed for that step. Does that make sense for everybody? You'll maybe get into it and have a couple questions, but honestly, by following each one of these, you're going to be doing a harmonic and you're going to be doing a cycloidal for the problems that you have. I think you'll make sense of it. Okay. If not, then that's what I'm here for. Okay. So that's as far as I want to go today, because I think that's enough for this first part, because the first part of these problems is what is a displacement diagram? So that by degree or by however many increments of degrees that you're looking at, you want to know what is your displacement. So we have to create that diagram first. So your problems that you would have, that you would be ready to look at, are going to be at the end of the chapter. The first one that you guys are looking at is going to be the homework problem 9-7. So we've got a cam drive is used for a mechanism that tests the durability of oven doors. The cam follower must rise outward 2 inches with harmonic motion in 1 second. Dwell for a half a second and then fall 2 inches with harmonic motion again in 1 second, and then dwell for 1 second. So there are 4 steps here. 2 of them have the harmonic motion and 2 of them are dwells. Okay. Then you're going to repeat the sequence. Determine the required speed of the cam, W, and graphically plot the follower displacement diagram. Okay, so that diagram that we're just looking at. In this case, it's going to be harmonic motion on both the rise and the fall. So if we go back to page 232, okay, this is going to be what you use. Okay, now as we look at the height, for instance, it looks like that's 2 inches, all right, on that height. So that means that over here, this is going to be a radius of 1 going around. This would be a full circle if it would continue on the other side, but you're just going to draw half of it. Okay. And then the corresponding numbers starting at the bottom going up to 6, and then from the left to right going 1 to 6. Correct. Correct. Yes, yeah, for cycloidal and for harmonic, yes, 6 sections. Now you could do more to get a more accurate spline, but 6 is enough, don't you think? If you want to do 12, you could. If you want to do 12, you could. It would just be a more accurate spline. Yeah. Yeah. Okay. Now the length along the x-axis, that's a little bit more arbitrary. Okay. Meaning you don't want this too narrow that you get, like you get really steep values, but you don't want it too long that they're stretched out so far. So if you take a peek at, for instance, like on page 236, example 9.3, if you look at this is 50 millimeters, okay, high. And what I've been noticing is that they're about 1, 2, 3 times the length of whatever the height is. You'll see that same trend on the first example that we looked at. So on page 227, here's our 2 inches, and this is about 2, 4, 6 inches long. Okay. So if you do like a 3 times the length of whatever your height is, that's a good place to start. I'm not saying it's going to be perfect, but it's probably a good place to start as far as divisions and how long to make that. Okay. And does it have to be 2 even increments? No. If I just find that to figure out how long this is going to be or what the amounts are going to be in between each one of these, it's easier to work with like even increments like 6 inches or 8 inches to figure out how many inches are in each one of the degrees, for instance. Okay. Any questions? You might not at this moment. Okay. But that's where kind of jumping in and working on these is where questions are going to come up. Okay. And that's what I fully expect. But first place to go is kind of back to the problem examples that we have here. And then also probably more importantly is going to be the construction circles. So on page 232 for the harmonic and on page 233 for the cycloidal. I think those are going to be helpful for you. Okay. All right. So that's the first problem. The second problem that you have to do is going to be 9.9. Okay. So at the bottom here, this cam mechanism, you're going to have a rise of 1 inch with cycloidal motion in 1.5 seconds. You're going to fall 1 inch with cycloidal and then dwell for a half a second. So just a couple of steps there as well. but then it's getting a look at how to construct with the cycloidal motion with that circle down in the corner. Okay. Now, in this case, you might say, well, if I'm rising 1 inch and falling 1 inch, can I just do a mirror? What's the answer? Why not? Different times, right? There's different times. So this one is 1.5 seconds you're going to rise in, and the other one you're going to fall. I'm sorry, you're going to fall in just 1 second. So you can't do a mirror of those. You might be able to use the same circle because the height or the rise and the fall distances are the same, but you won't be able to plot them horizontally the same. Okay. All right. Then that's where I'm going to stop today. The next time that we get together, then what we'll do is we'll add on and we'll look at creating the CAM profiles. Okay. Once we have these displacements done. Okay. All right. Any questions before I let you go? Okay.